Well, it's a great honor to welcome Robert Bryant to present our annual distinguished lecture. Robert is the current Philip Griffiths Professor of Math at Duke University, and he really needs no introduction, but I will say a few things anyway. Among his many honors, he was elected a Fellow of the American Academy of Arts and Sciences, a member of the National Academy of Arts and Sciences, a Fellow of the American Association for the Advancement of Science, and the American Math Society. As a first generation college student who eventually became the first openly
My
gay
AirPods don't work.
of the
I
American
noticed.
Math Society. Oh, I'm sorry, Sarah. He has been a very strong advocate for all underrepresented groups in mathematics. And on a personal note, I still remember one of the very first conferences I ever went to. I think Robert was either just finishing grad school or had just finished, and he was the conference was structured around his work, and he was giving a whole lecture series. And I don't think I've ever been at a conference where there was so much palpable excitement in the audience. So it's a pleasure to welcome him, and he will speak today on the affine Bonnet problem.
Thank you, Carolyn, for that very nice introduction. It's a great honor to be invited to speak in this in the Geometry with Symmetry seminar. It's this is these kind of conferences have been showing up more and more, and I think they're very valuable. It's a great chance to meet and talk with people that I haven't actually seen in quite a while. So today, what I want to talk about is an affine analog of a very classical problem in Euclidean geometry that turns out to have some very interesting features. That integrability and this approach actually solves some problems that have been surprisingly open for quite a while in affine geometry, and I thought it would be an interesting thing to talk about. So first, though, let me start by saying a little bit about the the classical Euclidean problem, which is which was addressed by Affine Bonnet in the 19th century. And let me set the stage for that. Of course, classical Euclidean surface theory attempts to understand the invariance of surfaces in Euclidean 3-space. And it centers on two local invariants that for any immersed surface, that is, if you start with an immersion of a surface in Euclidean space, the lowest order invariant under Euclidean transformations is the so-called first fundamental form, which is simply the dot product of the differential of x with itself. It's a quadratic differential form, and when expressed in terms of the local coordinates u and v, it has three coefficients: the classic E, F, and G in all the classic books. But of course, this by itself is not enough to determine x up to Euclidean motion, just the induced metric on the surface. And for that, you need to actually go to another invariant of the first order, that is the Gauss map, which is, of course, the cross product of the two partials divided by the norm. And I chose an orientation, so this makes sense. And once you have this other vector valued function on M, you can just take the dot product of the differential of x with the differential of the norm. And when you do that, you get a second quadratic form, the second fundamental form. And the theorem of Bonnet is that this pair of quadratic forms actually determines the surface up to Euclidean motion. But there's a little bit unsatisfying aspect of this, which is that in many ways, this is too much information because the immersion itself is locally, you can think of it as three functions of two variables, the coordinates of x expressed in u and v. But each of the quadratic forms, first and second fundamental form, are actually, each of them is actually three functions of two variables also. So you're actually getting out six functions of two variables to describe three functions of two variables. The only advantage of the six, of course, is that they're independent of Euclidean motion, which x by itself is not. So, for balance, there should be three relations on these six functions, and there are. These are the classic things that we study in curves and surfaces. There's one equation called the Gauss equation that relates the determinant of the second fundamental form. The determinant of the second fundamental form with respect to the first fundamental form, and says that that's actually equal to the Gauss curvature of the first fundamental form, which is, of course, while this is an algebraic function of this data, this involves two derivatives of the first fundamental form. That's one equation. It's an equation of two functions. But then there's an equation that's essentially a one form. That is, you take the divergence of the second fundamental form with respect to the metric induced by the first fundamental form, and that has to equal zero. That's the Cauchy equation. And this divergence is a excuse me, is a operator that depends only on the metric. And then you have the the satisfying Bonnet existence theorem that says that if the surface is simply connected and you have a positive definite quadratic form and another quadratic form that satisfy these three equations, then in fact they come from an immersion, and that immersion is unique up to Euclidean motion. What Bonnet asked was whether or not there was a way you could throw away some of the information of 1 and 2 and still get existence and uniqueness. And in particular, he asked, do we actually need all of first and second fundamental form to specify x? For example, would it be enough to know the first fundamental form and the mean curvature, which algebraically is the trace of the second fundamental form with respect to the first fundamental form, or half the trace? And that's still, of course, the first fundamental form and the mean curvature is now four functions of two variables. And so what you would expect is that there should be some compatibility conditions for the first fundamental form and H in order to determine whether or not they actually come from an immersion. And he wanted to understand what those conditions were and whether this was in fact enough to give uniqueness. So here is essentially what his approach was. One thing you notice for pure algebraic reasons is the square of the half trace minus the Gauss curvature is always greater than or equal to 0. I'm going to assume it's positive and write it as a square here. That is, I assume there's no umbilicus. And in terms of a local orthonormal coframing, omega 1 squared plus omega 1 and omega 2, so that you write I as omega 1 squared plus omega 2 squared, knowing H almost determines the second fundamental form once you know that the determinant of the second fundamental form with respect to 1 has to be R squared, has to be K, and you know the mean curvature. It determines it up to an angle, this function theta, that you can sort of rotate the trace-free part of the second fundamental form arbitrarily, and that won't affect the Gauss equation. But and that gives the general solution to the Gauss equation. But of course, you still have to have the Cauchy equation. So the Cauchy equation, when you take the divergence this way, like I said, it's a one form. And when you work this out, it turns out that it's R, which I've assumed to be positive, times this one form, where theta is, again, the unknown function we're working with, and the alphas are one forms that are computed from the data of omega 1, omega 2, and H, and their first derivatives. It's the algebraic formulas won't matter to us right now, but so I won't write it out. But so what Bonnet realized was that what you had to understand is it true that there is a theta that satisfies this equation? It's overdetermined, and because theta is a single function, this is a one form equation, so it's two equations for one function. And he asked, when is this formally integrable? When is there a solution? And the way you check that is if you take the derivative of both, the exterior derivative of both sides, of course, you'll get 0 on this side. And on this side, when you write it out using the fact that you know d theta, when you write out the exterior derivative, then you'll see that, of course, it's a 2 form times a function, and that function happens to be a linear combination of cosine and sine with and the function 1, where these functions capital A are computed from omega 1, omega 2 H and their first two derivatives. So just some expression. Some expressions, again, not particularly nice when you look at them in local coordinates, but we won't need to know what they look like. And anyway, formal integrability is then equivalent to these three functions vanishing. So that's three equations of second order on the data H and the first fundamental form. And here's what Bonnet did. He studied those set of equations, and he found out that if you have a quadratic form and a function, positive definite quadratic form and a function that satisfies these three equations, then there's actually two possibilities. One is sort of a very easy one, which is it turns out that if H is constant and and I is the first fundamental form of a surface with constant mean curvature, then A1, A2, and A3, capital A1, 0, 1, 2 are all vanish identically. And what that says is that, in fact, there's a says that there's actually a one parameter family of thetas that satisfy this equation. By the Frobenius theorem, there's a one parameter family of functions theta that satisfies this equation. So there's a one parameter family of deformations of the isometric deformations of the surface of a surface with constant mean curvature that preserves the mean curvature. And these are the so-called associated surfaces, the famous ones we know. For example, if H is 0, minimal surfaces, each minimal surface has a one parameter, has a circle, in fact, of isometric deformations as a minimal surface. So that's one way you can have it. The other way, it turns out, there's two different kinds of solutions. The second kind of solutions is, it turns out that there's actually, up to diffeomorphism, there's a four parameter family of data of pairs I and H that where H is not constant, and and they satisfy this condition, and therefore there's a one parameter family of ways of embedding these into with given mean curvature, isometrically embedding these with given mean curvature in Euclidean space. There were kind of mysterious surfaces. Bonnet could not actually write down what the surfaces were. He showed that they existed basically by an application of the Frobenius theorem. But it was kind of mysterious what the surfaces looked like, and it was, you know, the research on trying to understand what these surfaces look like was carried forward by him and Cartan and S.S. Chern. They wrote down they discovered quite a lot of properties of these surfaces and made them even more intriguing. But in fact, nobody knew what they looked like until late in the 20th century, when Bobenko and Eichner showed that this integrable system could actually be connected to a lax pair, and that you could actually eventually they showed that you could actually write the surfaces in terms of using theta functions and solutions of Panteley equations. And you can, I didn't import any of the pictures into the slides, but you can find the pictures on the internet. They're kind of weird. So they're transcendental surfaces. They're not elementary surfaces. That is, they're not, you can't explicitly write them in terms of elementary operations, but you can numerically integrate the things and get some good pictures. One of the things that comes out, although Cartan had already observed this, is that the surface actually, the one parameter family of diffeomorphisms actually turns out to be sliding the surface over itself. That is, deforming the surface as it slides over itself, so that you preserve the function h and the metric, so that the surface itself, unparametrized, is unique. It's just that there's a one parameter family of ways of sliding the surface over itself, is what happens in this case. It's very different from the minimal surface case or constant mean curvature case for associated surfaces. Whoops, what happened there? Anyway, back to what happens if the integrability conditions aren't satisfied. If the A's aren't zero, then the only way you can have a solution to this equation is if you want to, you can have at most two solutions theta of this equation, for exactly the same reason that you can at most have a line meets a circle in at most 2 points. And if the a1 squared plus a2 squared is bigger than a naught squared, then in fact there are two solutions theta, exactly two solutions. And so you could hope that those two algebraic solutions of this equation would actually satisfy the original differential equation, that is Caudatsi's equation. They don't necessarily, but if they do, then you actually get a pair of surfaces that called Bonnet mates, that are isometric and have the same mean curvature. They correspond there's a map between the two surfaces that that preserves the metric and the mean curvature. And Cartan showed that in fact the set of such surfaces depends on 4 functions of one variable. That's a and just for comparison, constant mean curvature surfaces depend on 2 functions of one variable, in terms of, when you count how much data do you get to specify in order to write down a solution. And Cartan showed that if you're looking for this more general thing where you don't have a one parameter family of Bonnet mates, but a single a pair of Bonnet mates like this, then they actually depend on 4 functions of one variable. And it turns out that in fact even this system can be interpreted in terms of pseudo-holomorphic curves and lax pairs, and there's quite a large literature on understanding these surfaces that have a Bonnet mate like this. So that's the Euclidean. That's a rough summary of the Euclidean story. I want to look at the corresponding problem in affine geometry, which doesn't seem to have been addressed until recently. And by affine space, of course, what I mean is 3 space where you're allowed to act on it by translations involving and preserving linear transformations. In other words, you only keep the volume, you don't keep the inner product. And the corresponding story in affine geometry is if you start with an immersion of a surface in the affine 3 space, you can define a second order invariant. It definitely depends on two derivatives by taking the u and v derivatives of x, and then take this quadratic second derivatives of x. Think of that as 3 column vectors. So 3 column vectors of height 3, you can take the determinant. That's affinely invariant once you tensor with du wedge dv. It turns out that that's the that's gives you an invariant that's actually, I think there's supposed to be a square there. Gives you a section of this bundle, sim2 t, the quadratic form times a volume form. And we put a non-degeneracy condition. We said that x is locally strictly convex if this quadratic form is definite. And in this case, which I'm going to assume henceforth, this quadratic form can be written as uniquely as a metric tensor. It's tensor the dual the area form associated to the metric. B looks like this, and you get this is what it looks like in local orthonormal coframing. And this quantity, this Ix is called the Blaschke metric associated to x, and it's second order, and as you might expect, it does not determine x up to unimodular affine equivalence. Just as the Euclidean metric didn't determine it. So what more information do you need to determine what the surface looks like? If you use the standard thing of expressing the differential of x in terms of Blaschke metric orthonormal coframes, E1 and E2, which are the dual frame field, you can put a restriction on the normal by requiring that E1 and E2 together with the putative normal has volume 1, because that makes sense in affine geometry. But that only determines E3 up to additive multiples of E1 and E2. However, if you put an extra condition, now that there's a unique normal so that you get the volume 1 constraint, and so that the differential of the normal is actually a linear combination of E1 and E2, which corresponds to the Euclidean case. And this n that's defined this way is actually third order in x. You have to differentiate when you work it out. So, but once you have a normal, you can write the normal as the differential of the normal, because it's a linear combination of E1 and E2. You can write it as E1 pi 1, E2 pi 2, and then write this essentially do the same dot product, even though where you're using the Blaschke metric to do the dot product, and you get a quadratic form. That's now fourth order in x. But the surprise, perhaps, is that this data does not determine the x up to affine unimodular equivalence. You can actually have surfaces with the same such data that are not congruent to each other in affine geometry at all. In fact, there's a lot of such surfaces. Well, what happens is that there's a missing third order piece of information. That is, if instead of going straight to the normal, to the derivative of the normal, you take the covariant differential of dx itself. Of course, because this is a torsion-free connection, this is a quadratic differential, vector valued quadratic differential. So you can write it in terms of E1, E2, and the normal. It turns out that the coefficient of the normal is in fact the Blaschke metric because of the normalizations that we chose. But then this Q1 and Q2 are quadratic forms. They depend on the choice of the coframing, but if you take Q1 tensor Q1 times omega 1 plus Q2 omega 2, the resulting cubic form is independent of the choice of basis, and it is a third order invariant of X. Now, Radon, in the early part of the 20th century, proved that in fact this pair, the first fundamental form and the cubic form, determine X up to unimodular affine equivalence. This is the analog of Bonnet uniqueness. But again, just as in Bonnet's problem, it's too much information. Quadratic form is 3 functions of 2 variables, and a quartic form and a cubic form is 4 functions of 2 variables, but the original X consists of 3 functions of 2 variables. So we should expect some compatibility conditions. And there are compatibility conditions. And again, there are 2 sets of compatibility conditions. One of them is algebraic, and which is that if you take the cubic form and you take the trace with respect to the Blaschke metric, you get 0. This is called apolarity, and that's 2 equations on the cubic form. So the cubic form is a section of a rank 2 bundle, sim3 trace 0, cubic forms with trace 0 with respect to the first fundamental form. But that's only 2 equations, and you need something else. And it turns out that Radon showed that there's actually an analog of the Cauchy equation, which is that there's a second order. There's a second order nonlinear operator defined by Ix, that when it's applied to C, it gives you a function, well, it's applied to anything in this trace 0 stuff. It gives you a function, so it's a single second order nonlinear elliptic equation that depends on the metric and the choice of orientation. And Radon proved the analog of Bonnet's existence theorem, that if you have a one connected surface and a positive form and a quadric and a cubic form, positive definite quadric and a cubic form that satisfy that the trace is 0 and Radon's equation, Radon's analog of the Cauchy equation, then in fact there is an immersion such that the first fundamental form and C are the ones given by this process. So that gives us uniqueness. That gives us existence, and uniqueness was up at the top of the page. So that's the analog of curves and surfaces, but for affine geometry, is specifying this quadratic form and cubic form, satisfying these conditions. And now you can ask the same question that Bonnet asked, which is, can you get by with less information than the entire cubic form? So, for example, you can look at the affine mean curvature, which is the trace, as just like in the Euclidean case, the trace of the second fundamental form with respect to the first fundamental form, and the analog of the Gauss equation tells you that in fact that this is equal to the Gauss curvature of the first form of Blaschke metric minus square norm of the cubic form, and so for example, knowing the affine mean curvature and the affine metric is equivalent to knowing the affine metric and basically the square norm of the cubic form, which is sometimes called the Pick invariant. It's known as the Pick invariant. And so the affine Bonnet problem is the analog of the Euclidean problem, is to determine when and in how many ways you can actually realize first fundamental form and a mean curvature by an affine immersion. Remember that it's overdetermined by one equation, just like in the Bonnet problem. because I has three coefficients in coordinates, and H is one more function. So it's four functions that are supposed to be determining three functions up to affine equivalence, unimodular affine equivalence. So you can start out the same way as Bonnet did, and write. It turns out that K minus H is the quantity, not K minus H squared, or H squared minus K, but in this case it's K, the Gauss curvature minus the mean curvature turns out to be, just for purposes of making everything work here, that 2 turns out to avoid any square roots. That's always greater than or equal to, this expression is always greater than or equal to 0, write it as 2r squared. And then, regarding what happens is that you get, when you write I as omega 1 squared plus omega 2 squared, then it turns out that you in order to specify C, you need only one more function. And that function is basically linear combinations of the two sections of the trace 0 cubic forms. So that's what we have with the coefficient of R. Once you factor out the R, those two coefficients with sum of the squares is 1. And and so what we want is, so theta at the moment, I mean, this just makes us, this is all you get for getting the trace condition. But now you got to satisfy Radon's condition, which is now 2 second order equations for theta, because you got to take this because of what I said earlier. It turns out I mean, this formula looks a little bit ungainly for C, but if you stare at it, you realize that it's actually the real part of this more compact expression, e to the I theta times R times omega 1 plus I omega 2 cubed. C is the real part. Now, if you write in local conformal coordinates, say a complex coordinate Z, write I as F times norm dz squared, then Radon's condition, when you write it out, becomes theta sub the second partial of theta with respect to Z is some explicit expression in terms of theta and theta sub Z, where the expression depends on the function F and the function H. F is this coefficient of I in coordinates. This expression is kind of a mess, but it's an explicit expression that involves things that are given to you plus the unknown theta and its Z derivative. And if it were formally integrable, if this equation were formally integrable, the analog of Bonnet's problem, then what you would do is you'd be able to, at one point, specify theta sub Z, and theta sub Z Z bar at a point, those 4 numbers, 4 because theta sub Z is a complex number, and there would be a unique local solution. That would be the analog of Bonnet's surfaces that have either constant mean curvature or this exceptional 4-dimensional family. But unfortunately, it turns out that this equation is never formally integrable. So you never can actually get a 4-parameter family of Bonnet deformations. And you find that out by just differentiating and trying to set all the conditions for the formal integrability to work, but it turns out they're just not compatible. So there always has to be more conditions on I and H in order to get when you sit down to do the calculation. However, it turns out, and this is something that I did a while ago, that if you have for given data I and H, then the sheaf of solutions, well, so there can't be a 4-parameter family. The next best thing that could happen would be that there would be a 3-parameter family of solutions. And it turns out that that is in fact possible, that you can actually get a 3-parameter family of solutions, but it only happens if H is constant and the curvature of the Blaschke metric satisfies this equation. That is, the Laplacian of log curvature minus H is, remember this quantity here is always greater than or equal to 0. That this Laplacian has to be 2H minus 6Ki, K sub I. So that's what happens in the most flexible case, and I'll say more about that a little later, because it's not at all obvious what these surfaces look like if they exist. I mean, it's not clear that they exist if you just if you sit down and first glance. But if you pursue this, I mean, this is sort of the best thing that could happen would be that there would be a 3-parameter family of solutions locally. But it turns out that there are examples of surfaces that have exactly a 1-parameter family of affine Bonnet mates. And we'll see an example a little later. What I don't know, and I've been spent a fair amount of time trying to figure out whether or not this is possible, is whether or not there's exactly 2-parameter family of affine Bonnet mates. It's right now the machinery that you would have to operate to do that. I mean, and I confess that a lot of these calculations were done with the assistance of Maple. No version of Maple that I know is capable of actually solving the algebraic equations that you would have to solve in order to answer this latter question. But there's always hope that some new idea could actually make some progress on that. I suspect there are 2-parameter families of solutions, but I don't know an example of one. But you can also ask the analog of Cartan's question, which is to try to classify the affine Bonnet mates. That is, you look for surfaces that have at least one non-congruent surface with the same Blaschke metric and mean curvature, affine mean curvature. And the analog of Cartan's theorem is that it turns out that they actually they do exist, and they depend on 7 functions of one variable. Whereas when you actually do the count here, up to diffeomorphism, the solutions of this equation, once you fix a constant h, the solutions of this equation for a Blaschke metric up to diffeomorphism, they depend on 2 functions of one variable. So there's a big gap between the things that have a 3-dimensional family of deformations and the things that only have essentially only one Bonnet mate. And there are things that do have exactly one mate, one non-trivial Bonnet mate. I'll give an example of something that has a 1-parameter family of solutions. This is a classical and well-known family of surfaces in affine geometry. Is you say a locally convex surface in affine 3 space is an affine sphere if its affine normal lines, that is, the lines that pass through the point on a surface in the direction of the affine normal, are actually concurrent or parallel. It's hyperbolic if its mean curvature is, which is necessarily constant, is negative. Otherwise, it's elliptic. And this is not a small family of surfaces in three space. For example, Cheng and Yao proved that every proper convex cone in affine three space has a unique complete affine sphere with h equals -1 asymptotic to that cone. So there's lots of them because there's lots of proper convex cones in A3. In fact, the affine spheres themselves depend on two functions of one variable. It's not hard to show that if you do have the data of a hyperbolic affine sphere, that is if this data, remember the I and C together determine it up to rigid motion, so you can tell whether or not from I and C you can tell whether or not the surface is a hyperbolic affine sphere. Then for any constant theta, you can you write C as the real part of this complex valued cubic form. Then then it turns out if you just multiply by e to the I theta, this is the analog of the minimal surface equation. When you rotate the second fundamental form in Euclidean geometry by a constant angle theta, you get the second fundamental form of another minimal surface with the same isometric minimal surface. It turns out this also works in affine geometry, just as it almost exactly the same way it works in Euclidean geometry. So you get these things with a one parameter family, but but you can check. It's not hard to show that if you take a generic hyperbolic affine sphere, then the only functions theta so that this satisfies the data of so that this actually gives you the data of an affine surface, so it satisfies Radon's equation. The only solution is that theta be constant. So this is the generic affine hyperbolic sphere is one of those examples where there's only a one parameter family of deformations. And I'll just say a little bit about the proof because I want to get onto one of the things that one of the ways that this study actually solved a problem that in affine geometry that was surprisingly unsettled. Is that the proof, the key to theorem 1 was realizing that the integrability conditions for Radon's equation can be written in the form of a lax pair, but a lax pair for the 10-dimensional Lie group sp2r, that is, it's the symplectic transformations in 4 space, which was kind of a shock when I noticed that, because what does symplectic geometry in 4 space have to do with affine surfaces in 3 space? It's kind of mysterious, in fact. And in fact, what I'll say a little bit more about that. What happens is that it turns out there's a kind of a twister-like construction that connects the Affine Bonnet problem with the geometry of holomorphic Legendrian curves in CP3 under the action of not sp2c, but sp2r, a real form of sp2c. And in fact, when you look at sp2r acting on CP3, it has open orbits, and inside those open orbits, they're kind of a kind of a unusual holomorphic contact homogeneous space, and it turns out that the generic holomorphic Legendrian curves can be used to construct solutions of the Affine Bonnet problem that have this 3-parameter family of deformations. And what an interesting thing about this is that you get a I just realized I'd not been looking at the chat at all. So I don't know if somebody has been raised a hand or asked a question. So please stop me if I'm not if I haven't responded to something you wanted to ask about. Here's an affine geometry problem that was studied relatively recently. Affine geometry has been studied since the 19th century, but you would think a natural question is, what are the surfaces that have constant k and h? You know, in Euclidean geometry, of course, we know the answer, and and they're all homogeneous. They're plane cylinders and spheres. But it turns out, kind of surprisingly, and this was discovered by Bryant and Dillon and their collaborators more than 30 years ago now, that there are surfaces with constant k and h in affine space that are not homogeneous. In fact, they need have no symmetries at all. It's kind of surprising, but in fact, you know, that if you go and look at their paper, they basically use the Frobenius. You know, a lot of calculations. They reduced it to a kind of a Frobenius kind of theorem where you get some overdetermined equations. You show they're consistent, but they couldn't actually integrate the equations. They're except in special cases. And so we knew that these surfaces that were quasi-homogeneous existed in affine geometry, but we didn't know what they looked like. And it was kind of mysterious. And if you go and look at the paper and look at how complicated the formulas are that they get, it's not surprising that you couldn't guess a solution. But once you know, but it turns out that in fact, so for example, a consequence of their work as far as existence goes is that there are 5 inequivalent affine surfaces with k equals -1 and h constant, and and in which case either h is -1, and that gives you a hyperbola of 2 sheets, or h is -3, and there are 4 inequivalent examples of those. By inequivalent, I mean affinely inequivalent, and 2 of which have only discrete symmetries. They have no continuous symmetries at all. But that was more or less what they got. Of course, they also did the non-convex case, but I'm ignoring the non-convex case in this talk. It's formally similar to the convex case. But now with realizing that, you know, if you look at the equations, if you look at this with h as constant, and then you look at the formulas that the formula for what k has to satisfy, it turns out it satisfies this condition for it satisfies the condition named in theorem 1 about the Laplacian of k minus h being 2h minus 6k. Satisfies that equation. And so that means that you can apply this twister-like geometry to actually explicitly write down what the solutions look like. And sure enough, that's what happens. And so you get a theorem that says that every connected locally strictly convex surface in affine 3 space with k and h constant either has k as h, that gives you the quadrics. In other words, they're totally umbilic, or after scaling has k equals h plus 2, and the first and third fundamental forms are locally equivalent to one of these 5 possibilities. That's what Dillon and Branken actually, of course, were able to integrate these because these all have a continuous symmetry. So they were able to figure out what these surfaces look like. This surface is a little bit mysterious, actually, but you can work out what it looks like. It again reduces to an ODE, but you can integrate it. But then these two surfaces are, this is it's locally parameterized by hyperbolic disk, and sure enough, there's the k equals -1 metric, and there's what the cubic form looks like. And you can see the cubic form because it has zeros and poles at the 6 vertices of a hexagon on the boundary of the disk. The the symmetries of the hyperbolic disk, having to fix these poles are trivial. Well, up to it's actually a what is it? There's a Z3 symmetry that because the zeros occur at the conjugates of the negative cube roots of 1. And fixing those points fixes the metric, fixes the motion. And then there's also a solution that is defined on the punctured disk and looks like this. And this is the maximal extent. In fact, once you have the formula, and you have this twistor kind of construction, you can actually explicitly integrate it. And so here's a surface defined by mapping the Poincare disk into affine 3 space with constant Gauss curvature -1, affine Gauss curvature -1, and mean curvature -3. And where H and G are these holomorphic functions on the disk. And you can, looking at that, you can see why it would have been fairly difficult to guess how you would integrate the equations. They have essentially no symmetry, but fortunately, twistor theory comes to the rescue to help you do that. I'll just conclude by giving the simplest case where you can actually write down what the solutions look like and see that there's a 3-parameter family of solutions. And that is, if you look at the case H equals 0, mean curvature 0, and now the equation we're talking about reduces to the Laplacian of the log of the Gauss curvature is -6 times the Gauss curvature for I. And in this case, this symmetry group sp2r can be reduced in a natural way to U11. And you can show that I can always, that if you have a disk, if you have a surface in affine 3 space that has this data, I and 0, then I satisfying this equation, then the first fundamental form can be written as the difference of different square differentials of 2 holomorphic functions, and the cubic form can be written as the real part of this expression, the exterior derivative of w as a function of z, circle z, dz, circle dz. And here's where the 3-parameter family comes in. You take a and b are complex constants, and take the numerator to be this guy divided by its conjugate. And of course, that means that you have to divide out by a real scalar. The multiplying a and b by a real scalar won't affect this expression. So you're looking at RP3 because you're taking 2 complex numbers that aren't 0 and dividing by a real scalar. You get RP3. And so the space of immersions, once you choose W as a function of Z on some domain, you'll get this metric, and the and the possible C's that can be realized, that you can realize with mean curvature 0, are in RP3, globally in RP3. And once you have this, especially because these are H is 0, it's an affine minimal surface, or as Calabi would say, an affine maximal surface, because it's a critical point for the area. Then Blaschke has a formula for affine minimal surfaces. It's an analog of the Weierstrass formula, and so you can just plug this into that formula and construct all the solutions to this equation. I mean, all the surfaces that have this, that satisfy this data in terms of essentially one holomorphic function of one variable. Okay, I'm almost out of time. I could go into more detail, but that's basically the picture. It's still, like I said, it's still mysterious what the, in some sense, what the two parameter families look like. And while I have lots, in fact, I think 4 different kinds of solutions that have a one parameter family, the affine sphere is one of them, but there are others. The full classification of even of the one parameter family of solutions is not known. And we don't know an example of a 2 parameter family, but I suspect they exist. Okay, I think that's all I really wanted to say, and I've just about run out of time. So let me end here, and if there are questions, I'm happy to answer. Right.
Thank you very much for a really interesting talk. Are there questions?
Renato and Alex. Yeah. Burnt, yeah. So who should we call on first? Renato?
Oh, okay. Renato, did you have a question?
Hi, Robert. No, I was just clicking the applaud button. Sorry.
Oh, I see. Oh, okay. Oh, it wasn't a question. Sorry.
Lovely talk. Yeah.
See, I saw the hand. I'm not seeing the big pictures. I'm seeing little ones, and I couldn't tell that it was a waving hand. Right. Yeah. Right. Or clapping hand. Right.
It's sort of so interesting that you found this sp2r action, and then it gave this link to these Legendre curves. And is there a sense of why it should be a link? Or
there is, if you look at that equation that I wrote down, let's see, the original equation, this theorem here, this equation, although I didn't recognize it right away, it turns out that you can rewrite this equation as a total lattice equation. And in fact, it turns out to be the total lattice associated to B2, which is one of the real forms of B2, which is, and sp2r is the B2 Lie algebra. So you could say that if I had been an expert in total lattices, I could have recognized this earlier, but I kind of had to find it by actually stumbling on the twistor theory construction, and then realizing the symmetry of the twistor theory was sp2r, and then you go around looking for why did that, how could that have happened? And so it made me suspect that this equation must be connected to some total lattice, and sure enough, it is. This happens a lot in these elliptic equations for surfaces, that these integrable equations turn out to be connected to total lattice of some Lie algebra, associated to some Lie algebra. But that's it written in this form. It's not completely obvious, but in fact, the clue is there if you know that that's what you're looking for.
It's really interesting how you found that. Wow.
Yeah. It was, I mean, like I said, I didn't recognize it right away. It was only after I understood this connection with holomorphic Legendrian curves in CP3 that I started, well, what could possibly have the symmetry of holomorphic Legendrian curves in CP3, and that you know, the SP2C seems like it would be the natural thing, but in fact, SP2C doesn't work. But SP2, this real form, this sort of non-compact real form of SP2C turns out to be the right object group, that the hidden symmetry of the equations.
There's a question in the chat. Let's see, will the recordings of this amazing talk be available? And the answer is yes, they will be posted, available on our website.
Yeah.
For the seminar.
And I'm hoping to have the paper out this summer. It's been hanging around for a while, but I'm just about finished being chair of the department, and I'm expecting to have some time to actually concentrate on finishing the paper this in July. My term ends on June 30th.
Great.
Yeah.
Are there any other questions or?
Yeah. Hi, Robert. It's Michael here again. So,
Hi, Michael. Yeah.
could you say something about the classification of quasi-homogeneous surfaces? This is in the, I guess you were talking about the unimodular case and strictly convex, but what about more generally?
You mean in affine geometry in general?
Yes.
Yeah. I mean when you say quasi-homogeneous, you mean, I assume you mean that there's an affine group acting quasi-homogeneously on the surface.
Yes.
Right?
Yes.
Yeah. So let's see. I think that classification, the homogeneous things were known, and I think, in fact, there's a paper, there's a set of lecture notes by Gary Jensen. I think it's in lecture notes in math or something like that. Basically it's lectures on affine surfaces, and he actually goes through. He uses the moving frame to go through and classify the homogeneous affine surfaces, the quasi-homogeneous, because they're not all homogeneous in the sense that, or said this way, there are homogeneous affine surfaces that you can close up and get a still a smooth surface, but they're fixed points in the symmetry group, so the surface is like quasi-homogeneous. But that list is known. Yeah.
Oh, okay. Thanks.
Yeah. But what's weird is that this is, I mean, the natural expectation would have been that if K and H were constant, then it would be quasi-homogeneous. But in fact, that's not true.
Yeah.
Are there any other questions? Well, if not, thank you again for a beautiful talk.
Oh, well, thank you for the invitation, and thanks everybody for your for coming to the talk in the ether, so to speak. Yeah, it's a pleasure. So.